A railroad wagon accelerates from rest as shown. Here's the railroad wagon, and it's accelerating. A small sphere of mass m is suspended at the end of a light string attached to the wagon ceiling at an angle of theta with the vertical. That's what happens when it's accelerating. So on this diagram here, draw a free body diagram of the forces acting on the sphere. Part B, determine the acceleration of the wagon, and determine the angle theta between the string and the vertical during the wagon's acceleration. So our free body diagram is pretty straightforward. We've got the weight of the sphere, mg, will always be directed downwards towards the center of the Earth. The sphere is attached to a string, so the force preventing it from falling will be the tension force. Tension force is always directed along the string. Now, when you draw the free body diagram with the forces acting on the sphere, you do not have to resolve them into the components. But since we want to start solving the problem, we're going to put it here. The vector for the tension force should be longer than the vector showing the weight of the sphere. Now, if you don't do that, that's not a problem. You're not going to get any trouble with that because you really don't know what it is until you solve the problem or think about it. Now, why does tension have to be greater than mg? Well, the tension force is angled while mg is straight down. When we resolve tension, we have t sine theta in that direction to the right, and you always have to pay attention which angle theta you're dealing with. Fortunately, it's up there. This one's going to be ft cosine theta. So since it's not moving in the up or down direction, you've got ft cosine theta has to equal mg. So if ft cosine theta equals mg, cosine theta is always less than 1. So tension has to be greater than mg. So when you multiply it by something less than 1, it equals mg. Find the acceleration of the wagon. Well, let's see. We're giving the time, and we have the velocity. Go all the way back to kinematics, well actually the unit right before this, and we get your initial velocity is 0. It starts accelerating, so v is equal to v0 plus at. v is at, divide both sides by t, and we have an acceleration of 0.5 meters per second squared. Determine the angle theta between the string and the vertical during the wagon's acceleration. We will go back to our free body diagram, and we'll determine which forces are acting in the same direction as the acceleration. We actually did that a few slides ago, but that's okay, we're going to do it again. The only horizontal force is the x component of the tension force, which is ft sine theta. See how this component here is opposite the angle? The hypotenuse is ft, so if you're opposite, that's ft sine theta. We need to relate the angle to the forces. We'll start with the x-axis. That's where the action's happening, right? We're accelerating in the x direction. So the sum of the forces in the x direction is ma subscript x. And what force do we have there? The only force we have is the tension force in the x direction, which is ft sine theta. So that equals our acceleration. And we've gotten rid of the subscript here because the given acceleration is a. There are two unknown variables, tension and acceleration, so a system of equations will be needed. Now we'll apply Newton's second law to the y-axis. There is no vertical acceleration, so a sub y is equal to 0. So the sum of the forces in the y directions equals ma sub y. Acceleration is 0. We've got the tension force up, gravity down. Put mg on the other side. And then what is the tension force in the y direction? It's tension cosine theta equals mg. We now use our system of equations to solve for the angle by eliminating the tension force. So here we go. Here's our x direction. Here's our y direction. We solve the y direction for tension force. It's mg over cosine theta. Plug that into tension here. We have mg over cosine theta times sine theta is equal to max. Max, of course, the acceleration in the x direction is just a. And here's one of the coolest trig things. Sine over cosine is tan. Okay, so we replace sine theta over cosine theta with tan theta. We have mg tan theta equals ma. Cancel out the m's. We have tan theta is equal to acceleration over g. Theta then is tan inverse of a over g. Plug in our numbers, and we get an angle of 2.9 degrees.